So now we have a complete system where A, B, C, and D are all non-zero values. So keep in mind, just as a side note, we could have multiple differential equations. We could have x prime, y prime, z prime, and as long as they're all linear functions of x, y, and z, we could use the same technique. And that's predominantly the reason why we're using matrices here, just to kind of summarize that basically it doesn't matter how many differential equations you have. You could excuse me, still use the same notation and write the fact that the y vector, excuse me, the dy dt vector matrix is equal to the A matrix full of coefficients times the x vector, which contains x, y, z, or whatever might be in there. So we can still use all that same notation. That's kind of one of the reasons why we like it. And so now we have the system, and let's just describe this in terms of two guys, and they own their businesses. We have Bill and Ted, and we have Bill's profit at time t and Ted's profit at time t, scaled in the appropriate units. You know, it could be millions of dollars or whatever. And so now we want to solve this thing. But we have no idea, because what we could do is we could just guess x of t and y of t and try to come up with some educated guesses for what these can be. It's hard enough with two equations with two unknowns. The other one had two equations, two unknowns, but one of the terms was missing, which gave us a nice trivial solution that y could be 0. But you know, x and y both 0 would work, but that doesn't help us, right? Because if x and y are both 0, that's a very boring solution. That doesn't give us any additional information about their profits. So it's hard enough to guess 1, but now try to get 2. And remember, we need 2 because of the linearity principle, which says that in order for me to get satisfy initial conditions, I'm going to need 2 arbitrary constants in order to be able to do this. And I need to be able to solve simultaneously for both of them in order to be able to satisfy my initial conditions. It's not good enough just to find 1 unless that vector happens to be a multiple of 2, 1. Okay, well, what we might want to do is just sort of investigate the behavior of this function and see how this looks on a phase plane. So there it is on a phase plane, and it might be kind of hard to see. I know something you don't know based upon this, but there actually appear to be, like right along here where my cursor is running, there appears to be a straight line, and it almost appears as though that straight line is following in one direction. So there's I don't know if that was the one I was pointing at. That's the one I was pointing at. You notice that for an initial condition of 1, 1, this guy produced a straight line solution. That goes back in the opposite direction. So let me change my initial points here. I'm not showing them to you just yet because we'll discover how we can find these. So there's one, and there's also another one, and this one might be a little bit hard to see, but it goes right about through there. Right about through there somewhere, and there it is. And then it also continues on through the positive plane. And you'll notice that what's significant about these solutions, again, these are just for 4 different initial conditions, these are produced, is that if, for example, you start at a profit of here, then it looks like x and y are both projected to increase, and the farther you get away from that point, the faster these flow lines go, and or indicate that, you know, it kind of goes like this and then speeds up. And similarly here, that if you start off with this positive profit, then your both profits are expected to soar incredibly high, and similarly between here. But depending on which of these 4 kind of pseudo quadrants you fall in, the behavior is much different. Right here, all the solutions seem to veer away in this sort of circular fashion. Here they kind of seem to jet out, and as long as we have existence and uniqueness, then no solution should cut through either of these. And here, kind of again, you get that circular flow away. There's a little bit of downward movement and then movement away. So what we want to talk about here for a second, and you'll see why later. This is going to be kind of unintuitive as to why we're doing this, other than we get to kind of see how the pieces fit together, is that we want to basically say, how would we model these straight line solutions? What is significant about a solution on this straight line? Well, I'll tell you one of them. This guy actually has the initial condition 1, 1. Okay, so if I look at that initial condition of 1, 1, then what do I know about every single vector related along that same solution plane? Well, Well, if 1, 1 is the vector from 0, 0 to that point right there, then every single vector, for example, if I were to continue on, every single vector points in the same direction, right? So 1, 1, even though 1, 1 is a vector that stops there, that's its magnitude, its direction is the same as the vector 2, 2, is the same as the vector 3, 3, is the same as the vector 4, 4, is the same as the vector 5, 5, and so on. So every vector along that straight line solution is of the form some constant multiple of 1, 1. And certainly we could say, well, that k could also be negative because we're also talking about vectors that point in the opposite direction, but it's still along that exact same straight line. They're all vector multiples of 1, 1. So as they get farther out, a vector here, maybe that's a vector that would be, if you were to center it at the origin, it would be the vector 2, 2. And as they get farther out, 3, 3, and 4, 4, and so on. And so every single vector is a multiple of the vector before. Well, what is this vector? Well, this vector is a slope, right? This is a slope. And each other slope is a constant multiple of that slope. Okay? Well, how do we indicate slopes? Where do these slopes pop out of? Well, the slopes pop out of our dx dt and our dy dt, right? So we're saying that the slope is always proportional by some constant. We're going to call that constant lambda. That's a Greek symbol. I'm going to call it lambda. No special reason other than that's just kind of customary. And what is it a constant multiple of? Well, it's a constant multiple of whatever vector we plug in. So every vector is a constant multiple of the x vector. So if the x vector is, like this is the x vector right here. This is the x vector, 1, 1. Well, how else do you indicate the slope? You indicate it by saying ax plus by cx plus dy, right? That's just another way of saying dx dt dy dt, and that equals lambda x. Okay, well, if I write my matrix notation, this we've rewritten as just ax. I should kind of make this look more like a vector. And we're saying that ax, the slope that pops out of this calculation, is going to be some constant multiple of the vector we plug in, right? Because in other words, if I plug in 1, 1, which happens to be a vector along this line, then what am I going to get? Well, I'm going to get some constant multiple of 1, 1, right? So every slope, the slope calculation at every point is going to be a constant multiple of the slope at that current point. So if I calculate the slope here, that's going to be a constant multiple of the vector right before it, which is a constant multiple of the vector right before it, which is a constant multiple of the vector right before. Again, I'm kind of rattling on here, but this right here is the equation that will help us. We can actually determine what lambda is. In other words, what is the slope getting multiplied by as you increase the vector x? So again, x, remember, consists of an ordered pair. It's x, y. So it can be thought of as an ordered pair, and it can be thought simultaneously of a vector that, again, okay, let's think about these as ordered pairs now. If I calculate the slope at the ordered pair x, that's going to be some constant multiple of my ordered pair. Again, if I'm at 1, 1, then the slope there is going to be some constant multiple of 1, 1. So now the question becomes, one, we need to know lambda, because if we know lambda, then we know what, at each point, how big the slope is. It's going to be some constant multiple of that slope. So in other words, we need to figure out what these guys are going to be. Well, let's see how this would work. So ax, which is ax plus by, cx plus dy, is equal to, and I'm just going to write two separate equations. All right, lambda x. What is x? Lambda x would be lambda times xy. So that would be lambda x. This would be lambda y. Okay, well, I need to solve for x and y, so one thing I'll do is I'll just move it over to the other side. So I'll have ax minus lambda x plus by equals 0. And then I will also have cx plus dy minus lambda y is equal to 0. And I'm just kind of lining things up here. Okay, so one way I could isolate the x term is 1 by factoring out an x from this term, so that would give me a minus lambda times x plus by equals 0. And then cx plus d minus lambda y equals 0. And now I need to figure out what these values should be. Now the mathematical key is to ensure that we have, because what we're going to do is our next process, or part of the process, and you'll see why we need to find this vector, but we will need lambdas, and you'll see that there can be more than one, and then we'll need a vector x, y. Okay, well, I'm eventually going to have to solve for x and y here, and if I don't have the right setup, then I may end up having the trivial solution 0, 0. So that might not mean much to you right now, but we're going to need to, for each lambda that we calculate, we're going to need to find this vector, this special vector, which has a special name. It's called an eigenvector. We'll define that in a few minutes. And in order for this vector to not be non-zero, we don't want, again, a vector of 0, 0. We will ensure, the key is, find lambda so that the determinant of what we've calculated here, which, what have we calculated? We have calculated, so this side is ax, and then this side is lambda x. So what we've done essentially is we've subtracted lambda x from both sides, and then we're going to find the determinant of that result. So one thing we could also do is write this as a minus lambda times x and factor that vector out. So we want the determinant of that to equal 0. So that xy is non-trivial. Do we get to do that? Do we just get to make that up? Absolutely. We get to just specify lambda so that it's non-trivial. Well, what would that mean? Well, that would mean that, in other words, i.e., a minus lambda, remember it's the cross product, it's this times this, so that's a minus lambda times d minus lambda, minus this times this, c times b. And so what that really boils down to is if you FOIL it out and solve for lambda to get it equal to 0, then you'll ensure that the system of these two equations has a non-trivial result. Okay, so let's try with our example. With our example, we have, well, what do we have? We have 4x minus 2y, x plus y. So dx dt equals 4x minus 2y dy dt equals x plus y. So by the way, it looks like both these guys are doing pretty good in business, right? He's adversely affected by what's happening over here, but if x starts off sufficiently large, then Bill's profit might be constantly positive, and if y, regardless of what x and y are, as long as y is not negative, or x and y are not negative, then we're going to experience growth for Ted at all times. Okay, so in this case, let's go back. So we want to ensure that ax equals lambda x. So again, we're looking for these straight line solutions. Why are we looking for them? You might say, well, Milos, you showed it to us on the graph, but why do we care about those straight lines? Well, it turns out they have some special mathematical properties that we'll see in a moment. Okay, so what does this mean for us? Well, a times x is really just that and that, and I'm going to write it in equation form. But again, keep in mind this can be thought of as a matrix, equals lambda x lambda y. Again, this is the x vector. These are the values in that vector. And so what I find is that I have 4 minus lambda times x minus 2y, and that equals 0. And then x plus, in this case, this is a 1, so that'll be 1 minus lambda y is going to equal 0. And now my determinant, my determinant is going to be 4 minus lambda times 1 minus lambda minus, well, this is a negative, so we've got to be cautious there. That's going to be 1 times negative 2, which is going to leave us with, well, we want to FOIL this out because we want to solve for lambda, or at the very maximum, we could graph this and figure out what lambda has to be. We could just make this look like 4 minus x, 1 minus x, negative 1 times negative 2. Again, we want this determinant to be 0, so we force it to be 0, and we find that corresponding lambda. So what I will do is I will actually go over to Wolfram Alpha, and I will solve this so that we don't have to spend the time. But again, you can solve this with your calculator, find the zeros of this function, and do it that way. Okay, so here I am, and I'm just going to enter in 4 minus, I'm not going to use lambda because I don't know how to find a lambda on here very easily. 1 minus x minus 1 times negative 2 equals 0. And it should fairly quickly give me those solutions. Keep in mind that this is a quadratic function, right? So it's not the case that these solutions will exist all the time. Imagine that this parabola were shifted up a little bit. Now you would have lambdas that are imaginary, and that is going to pose a little bit of a problem to us in the future. So that means that it says that lambda has to equal 2 and 3. Okay, so lambda equals 2, and I'll just say lambda 1 equals 2, lambda 2 equals 3. And these guys are called eigenvalues. Eigenvalues. And traditionally people use lambda to denote eigenvalues. There's no other great reason. So what we wanted, our next step was going to be, we will need to find lambdas, a vector, and for each lambda a vector xy. Okay, so let's just start for these vectors. So what these vectors are called, since they're using the eigenvalues, these are called the eigenvectors, and we're going to call these v1 and v2 for vector 1 and vector 2. And the way these are calculated is basically now if lambda 1 equals 2, so I'll start for case 1, lambda 1 equals 2, then that gives me, well, what was my equation again? It was 4 minus lambda x minus 2y. So 4 minus lambda x minus 2y equals 0. And then my second one was 1x plus 1 minus y. 1 minus lambda, which in our case is 2, y equals 0. And so this gives me 2x minus 2y equals 0, and it gives me x minus y equals 0. So those are my two equations now, my equations based on this particular eigenvalue, based on what we call the characteristic polynomial, and that's where we had to solve for our lambda. That thing was called the characteristic polynomial. Okay, so this is great, but notice now that this equation and this equation are exactly the same equation. It's vectors, excuse me, vectors 2, negative 2, 1, negative 1. This guy here, if I took this guy and I multiplied it by 2, I get exactly this guy. So if I plot them, they're exactly the same equation. Subtract 2x from both sides, divide by negative 2, you get y equals x. And then same thing here, subtract x, divide by negative 1, you get y equals x. So they're the same equation. So how the heck do I find a solution if they're the same equation? Well, that's just the thing. They have the fact that they're that we have determinant of ax minus lambda x, since that equals 0, implies that we have infinitely many solutions. So how do we list that out there? Well, we'll just pick an equation. Pick one equation, whichever one you like. I'm going to pick x minus y equals 0. And this is just going to give me a relationship between x and y, right? So if I solve for one variable or the other, I get y equals x. Okay, so that means that if x increases by 1, y increases by 1. So give me any one vector that is such that y is equal to x. All right, well, if I look at a vector, 1, 1 satisfies y equals x, 2, 2 satisfies y equals x, 3, 3 satisfies y equals x. Whatever you pick for x, if I pick x equals 1, then y equals 1. If I pick x equals 2, then y equals 2 because of the relationship y equals x. So which one do I pick? Do I pick 1, 1 or 2, 2? Well, it turns out it doesn't matter because my original straight line solution said that ax equals lambda x. Okay, so in other words, if I take any vector and I multiply it by, if I take any vector with this lambda, so 2x, and in this case my a is basically my 4, negative 2, 1, 1, I don't know what that is, times 1, 1, that definitely satisfies this equation. That basically if I plug in, if I'm at the vector 1, 1, or I'm at the point 1, 1, the slope at that point is going to be double whatever my vector is. Again, so if I plug in the vector 1, 1, then the output is going to be double my 1, 1 vector. And also notice that I told you earlier that this vector here has the initial point 1, 1. So we've in fact satisfied it. We've in fact found that basically a vector on that line, and so now every other vector is just a constant multiple of that vector. So again, 2, 2, if I plugged in 2, 2, that would tell me the slope is twice whatever vector I'm currently at. And so notice that this pans out that you get 4 times 1 is 1, negative 2 times 1 is negative 2, 4 minus 2 is 2, 1 times 1 is 1, 1 times 1 is 1, add them together you get 2, and that is in fact the case that 2, 2 equals 2 times 1, 1. So I found basically that each vector is double, or the slope at each vector is double whatever the values of my vector are. So we found out that for lambda 1, it doesn't matter what you call them, lambda 1 or lambda 2, if lambda 1 is equal to 2, it has an associated eigenvector of 1, 1. Again, you could have used 2, 2, or even negative 1, or 3, 3, or whatever you wanted to, because it turns out that later on we're going to actually end up solving for some constants that will adjust for the initial condition. All right, so for lambda 2 is equal to 3, and I'm going to repeat that same thing. I'm going to have 4 minus 3 times the x vector, minus 2, whoops, take that back. 4 minus 3 times x minus 2y equals 0. And then I had 1x plus 1 minus my eigenvalue y equals 0. And you're going to again notice that the reason we've chosen this is because these two lines are the same line. In fact, in this case, even the coefficients work out exactly, so you can see that again they're the same based on the fact that we solved to ensure that that determinant is equal to 0. So that helps justify why the determinant must be equal to 0. And so again, we're going to solve this. Pick whichever equation you want. Obviously, they're both the same. But x minus 2y implies that negative 2y equals negative x, and that implies that y equals negative a half x, or negative x over 2. Okay, so again, if I pick whatever I pick for x, let's just say I pick 2 for x. And why did I pick 2? Because it's a nice number. I don't get any fractions or anything like that. That means that y is equal to negative x over 2, which means y would be negative 1. So every vector along, let's see here. So if from here I also could have picked negative 2 for x, and then I would have gotten positive 1 for y. But basically, we're saying that if you go, excuse me, this should be positive here. Let me erase that negative sign, because we divided by negative 2, and that made the negative go away. So basically, if we look here and we say, all right, we'll go over 2 units, that takes us up exactly 1 unit. And that's a vector along that straight line solution again. Same thing this way, if you look at a vector that's negative 2, then you go down -1 and you fall along that straight line solution again. So every single point along this is some constant multiple of 2, 1. -2, -1, or 2, +1, or 4, 2, or 6, 3, and so on and so forth. So to keep this simple, I'm just going to let my eigenvector be represented by 2, 1, because that's the simplest possible thing I could think of. You don't want to use 0, because obviously 0 you have x equals 0, y equals 0. So this means for lambda 2, which is the value 3, I have the associated eigenvector v2, which is equal to 2, 1. Again, you could have picked 4, 2, or 6, 3, or whatever, and we're still going to end up with the same answer in the result in the end. So that's the process of we've basically identified eigenvalues. Let's back up a second before we stop this video. I know it's a long one. I apologize. We basically said we're going to find the straight line solution that we noticed in the phase plane. We noticed that every single vector is a constant multiple of the slope at that vector, that basically all the slopes point in the same direction. Now, we wanted to figure out what lambda had to be in order for us to figure out, what each vector how much bigger or smaller, by what factor does that slope get. So we said, all right, we're going to need to know lambda. So we found lambda, and we figured out that in order for us to have a meaningful vector, an eigenvector, we would have to ensure that the determinant is 0. Because if the determinant is 0, then you have more than just a non-trivial solution. This is the determinant, how you would write it out, a minus lambda, d minus lambda, minus cb equals 0. And in our example, we just calculated this, 4 minus lambda, -2, 1, 1 minus lambda, solved the determinant, ensured that it was 0 by finding the correct lambda 1, lambda 2. And then for each lambda, we plugged each lambda back in to figure out what the associated eigenvector was. The eigenvector, again, just told us basically the direction in which that vector had to point. So the eigenvector, the first one, pointed in the direction of 1, 1. And so what that ensured is that every time we found a constant multiple of this, the next slope would point in exactly the same direction. We did the same thing, so we calculated, and we like to just keep our eigenvector as simple as possible. So again, you could have plugged in x equals square root of 2, and then y would have been the square root of 2, but who likes to do that? You can pick these to be simple, because when we later on solve for constants, that will scale our solution appropriately, and we'll all get the same answer. Then we did the same thing for lambda 2, figured out our associated eigenvector, which was basically a constant multiple of 2, 1. You could have picked 1, 0.5, whatever, but 2, 1 was, I think, the simplest one to use. Again, you don't want to use 0, 0, because that's a trivial result. It works, but it's a trivial result, and it doesn't tell us which direction these point in. So the eigenvectors just tell us which direction our straight line solutions point in. The eigenvalue tells us that at any one point, like there, if I calculate that, and that's the point 2, 2, and I plug in 2, 2, the vector, into its corresponding ax equals lambda x, then it tells me that that vector gets doubled, and now the slope going this way is twice as fast as it was when it hit that point right there. So the next video we'll talk about, well, how do we use these results to now construct a solution for a general solution for any solution in this, maybe that one or one of these guys or one of these guys. How do we get those based upon knowing the straight line solutions?